Hello, this is Mr. A again. This time I have a question on efficiency and we will solve this together. So let me go ahead and start by reading the question. An electric motor operates a pump that irrigates a farmer's crop by pumping 1.0 times 10 to the power 4. That is an exponential. I don't know if I could change it, but I will try. 10 to the power 4 liter of water, a vertical distance of 8.0 meters into a field each hour. That each hour is important. So we need to remember that this thing is happening each hour. Let's highlight that a little bit. Okay, the motor has an operating resistance of 22.0 ohms and is connected across a 110 volt source. And there are two parts to this. There are two questions. First part is what current does the motor draw? And the second part is how efficient is the motor? Okay, so let's start with the current part, which is fairly straightforward and direct. Um we just apply Ohm's law. In order to find current, we apply Ohm's law, which is I equals V over R. I is the current, V the voltage, R the resistance in the circuit. And from that, since we already have the voltage as 110 and the current as 22.0, um, the resistance as 22.0 ohms, the current comes out to 5.0 amperes. Okay, so that's, like I said, simple and straightforward. The second part asks for the efficiency of the motor. Now, efficiency by itself can be defined in, uh, different terms. It all has to do with the way the energy is being consumed or how much energy that a machine or a system consumes is set out as work. So when something converts energy into work, uh, we can talk about its efficiency as a ratio of those energies or the work done and the energy used and so on. So I have set out a few statements here, a few fractions. So efficiency is defined in various ways, such as you can have work done divided by energy used. You can have energy output over energy input. You can have power dissipated over power absorbed for the same duration. So remember, when we speak of power, since power is basically just energy per unit time, so the time here becomes relevant. The power used and the power expended will not correlate unless we are talking about the same amount of time. So, in other words, we are just really talking about energy. Even when we say or use the word power, we are really just talking about energy because we're keeping the time constant. Okay, so the important thing to remember about all this is that nothing completely converts energy into work. No real machine absorbs a certain amount of energy and then outputs the exact same amount of energy. There's always some energy that is used up in the process. There's always some energy lost in the system, in the surroundings, in whatever. So the work done is always less than the energy used. So you always have to keep in mind that the fraction, your ratio should work out to less than 1. So the top part is always the lesser quantity and the bottom part is the greater quantity. So what you input into a system is always greater. What you get out of it is always less. No real machine is even 100% efficient. It's always less than 100. The more the value, the closer it is to 1, the more efficient the machine is. The closer it is to 0, the less efficient the machine is. But it is never equal to 0 and never equal to 1 in real terms. Because if it's 0, then basically it's not really a machine at all. You're not doing anything. So anyway, so that little bit needs to be understood. And as a general rule, efficiency is expressed as a percentage. Like I said, it's a ratio. So once we get the ratio, whatever the units are for the numerator, the same units are for the denominator. Since we're taking ratios of similar quantities, the units will cancel out. You get a number, and that number should be between 0 and 1. So, as a general rule, we express that as a percentage. It just looks better. So, efficiency is expressed as a percentage, which means whatever number you get, you multiply by 100% and you get whatever percentage. Okay, so that's just a little bit of preamble, if you like. And so let's go ahead and proceed. Uh, One thing that is always important is to have units expressed consistently. When I say consistent, I mean in the same set of or the same system of units. So if you have units in the CGS system, which is centimeter, gram, second, then all your units should comply. If you have your units in the FPS system, which is foot, pound, second system, then all your units should comply. So you must not have, say, time being measured in hours and distance measured in meters, and then you have say an area measured in square feet and so on. That is not allowed. That is you're mingling units, and that does not work. So it's always easier if you express everything in SI units, because most of your equations are worked out in SI units, and sometimes the values are not exactly the same in all units. And so, as a safe precaution, if you convert everything to SI, you will be safe. All right, so let's proceed. Uh, Mechanical power, is equal to uh, potential energy over time. I use potential energy in this case because the water is being shot up vertically, and so it is gaining potential energy. If something was going and we were dealing with its velocity, etc., we would probably use kinetic energy. Just depends, because we need to find the energy, and here we have a vertical height and we have a volume of water. Then the safest, best way to do it is to use, um, like I said, use potential energy. So power equals potential energy divided by time, because power is always energy over time. And how do we find potential energy in this case? We have volume. Remember, for potential energy, the formula is mgh. M is mass. If you have the volume, to find mass, you must use the density of the substance. And since this is water for irrigation, the density is assumed to be 1000 kilograms per meter cube. So it's not one in this case, because we're using SI units. And in SI units, it's 1000 kilograms per meter cube. So the density is 1000. The volume is given in liters. And again, liters are not SI units. So you have to convert that to meter cube. This is 10,000 liters. And if you divide that in by 1,000, because there's 1,000 liters to a meter cube, you get 10 meter cube. So volume is 10, and between the rho and the V, by when you take the product, that is equal to M, because density is mass over volume. So density times volume is equal to mass. And so in this equation for potential energy, we are using rho times V as the value of mass, times G, which is 9.81, times H, which is given as 8.0 meters. Okay, and then the time, remember we mark time as 1 hour, because this is the event occurring every hour, each hour. But the SI unit for time is not 1 hour, it's a second. And so we divide by 3600, or the number of seconds, and we'll get power in watts, which is the SI unit for power. All right, so let's plug the numbers in. You have 1000 times 10 times 9.81 times 8.0 uh, divided by 3600 gives 218 watts, which is the same thing as saying 218 joules per second. Why have I written it like this? Just so you understand that as long as both events are taking place over 1 second, It's the number of joules that you're comparing, and that is the SI unit. And so uh, we can compare joules right here, and of course the units will cancel out eventually. So when we do the efficiency, it really wouldn't matter whether it's joules or watts or whatever. Okay, so that is the power output, because that is the work being done on the water. It's being shot up 8 meters, and the mass of the water that is being shot up every hour is 10,000 kilograms. Is that right? No, the mass that is being shot up is, yeah, 10,000 kilograms. All right, so then the power input, which is what the motor is doing, it is providing the energy. And what is the power of the motor? Power is equal to current times voltage, that is 5, which we calculated up here, times 110, which is given, and you get 550 watts. Did I get that right? Yeah, 550 watts. Or we can express that as 550 joules per second, just like we did over here. And so now we take the ratio, energy output, energy input, or work done over energy input, and that ratio then multiplied by 100% gives us the efficiency. So you have 218 divided by 550 times 100% gives 39.6%. If you did not do the 100%, you would get 0.396. That would be your fraction, 0.396. Actually, the 6 shouldn't even be there. It's just two significant digits. 3 over here, 2 over here, 2 over here. Yeah, it should just be 40, really. So I'm going to make that little correction here. It's 40%. Oh, that is not good. 4.0 times 10 to the power 2. That would be the way to express it. Because 40 would be only one significant digit. Our answer should be 2. And so that's what we do. 4 times, am I doing that right? 10 times 2, no, 1. 10 to the power of, there. So that is your efficiency, 40%, or because it's supposed to be two significant digits, it's 4.0, that's two significant digits, but then the value is not 40, it's just 4. So you put a 10 to the power of 1 to express it as a percentage in two significant digits. Okay, so that basically is the answer to this question. The current is 5 amperes and the efficiency of the system is 40%. Okay, so if anybody has any further clarification that they need on this one, please make sure that you send me a message. And also remember that I do provide one-on-one tutoring if you need help. So let me know. All right, and this is Mr. A signing off.